The early universe was a nearly uniform plasma, yet today, matter is bound into highly ordered, complex structures, galaxies, stellar nurseries, and planetary systems. This local complexity appears to violate classical thermodynamics. In 1865, physicist Rudolf Clausius established that the total entropy of the universe must always increase. Isolated systems invariably decay toward maximum disorder, a terminal state Clausius called the heat death. If the laws of physics demand an inexorable slide into chaos, a cooling cosmos should not spontaneously forge the extreme order required for stars and biological life. The resolution to this paradox lies in the unique behavior of self-gravitating systems. When a uniform gas cloud experiences a slight density perturbation, it does not passively diffuse. Heat flows from the contracting regions outward to the expanding regions, driving the system further from equilibrium. This occurs because gravity possesses a negative heat capacity. According to the Zerial theorem, kinetic energy in a gravitationally bound system is inversely related to its total energy. A loss of total energy actually causes the system to contract and heat up, separating into a highly compact, low-entropy core, a star, and a massive efflux of high-entropy radiation. The formation of the star represents a localized drop in entropy. However, the radiation ejected into the void creates an increase in surrounding disorder that vastly outweighs the local ordering. The second law is strictly maintained. Gravity utilizes this thermodynamic decay. By forcing matter to collapse, it extracts usable work, briefly spinning up highly complex structures on the long, inevitable road to thermal equilibrium. To map the eventual exhaustion of these structures, astrophysicists rely on a logarithmic scale of cosmological decades, where each unit represents a tenfold increase in time. The driver of activity across this timeline is the entropy gap. This is the quantitative difference between the universe's actual entropy and the theoretical maximum entropy it could possibly hold. This theoretical ceiling is determined by the Bekenstein-Hawking entropy of the cosmological event horizon. Because the universe is expanding, this boundary grows. The maximum possible gravitational entropy increases at a significantly faster rate than the entropy inside it. This map of the cosmic microwave background represents the bulk of our universe's actual entropy, trapped primarily in diffuse background radiation and supermassive black holes. The upper bound grows faster than the internal entropy, continuously pulling the ceiling from the floor. Space itself stretches, preventing the system from achieving thermal stasis during its expanding phases. Every stellar ignition, every thermodynamic cycle, and every biological metabolic process functions strictly by draining this evaporating reservoir of free energy. We currently reside in the Stellarcirrus era, between cosmological decades 6 and 14. We have already passed peak hydrogen. The raw material for stellar genesis is finite and actively depleting. High-mass stars burn through their fuel in a few million years. Low-mass red dwarfs are far more conservative, extending their lifetimes to trillions of years. Yet by the 14th cosmological decade, the last red dwarfs will contract into white dwarf, and star formation will permanently cease. The universe transitions into a degenerate era. The cosmos becomes a frozen expanse populated exclusively by dead stellar remnants, brown dwarfs, white dwarfs, neutron stars, and black holes. Ambient temperatures approach absolute zero. Tightly bound planets orbiting degenerate hosts continuously bleed energy through gravitational waves, spiraling inward until torn apart by tidal forces. Conversely, close encounters with interloping stellar remnants disrupt wider trajectories, slingshotting them into the void as rogue works. Projecting the physics of the next epoch requires a specific condition, the absolute stability of the proton. If protons eventually decay, ordinary matter dissolves into radiation. If they do not, matter faces an even longer quantum dissolution. The familiar architecture of planetary systems ends in scattering and orbital degradation, stripping celestial bodies from their host stars and dispersing them into an expanding, dark volume. In a universe where classical thermal fusion has ceased and ambient temperatures rest near absolute zero, the timeline extends into hyper-astronomical scales, governed entirely by quantum mechanics. Pike nuclear reactions allow elements within degenerate remnants to bypass Coulomb barriers via quantum tunneling over hyper-astronomical timescales. Lighter elements undergo cold fusion, inevitably transmuting all degenerate matter into perfect cold spheres of pure iron-56, the apex of nuclear binding energy. These iron stars achieve absolute peak nuclear stability, but they harbor a mechanical flaw. Their structural integrity relies entirely on electron degeneracy pressure to counteract the crushing force of their own gravity. Pick nuclear reactions alter internal chemistry, lowering the electron fraction. The Chandrasekhar limit scales with this, dropping the star's maximum supported mass. Once this limit falls below the star's actual mass, degeneracy pressure fails. It undergoes a catastrophic collapse, erupting as a black dwarf supernova. The timeline guarantees that atomic structure has a fixed expiration date. Degenerate matter slowly deletes itself, ensuring ordinary matter is entirely scrubbed from the cosmos. The iron star timeline assumes the vacuum of space is stable. However, the Higgs boson mass suggests we may reside in a metastable false vacuum. If so, quantum tunneling could nucleate a bubble of true vacuum that expands at the speed of light, instantly obliterating existing physics. This false vacuum decay would rewrite the fundamental constants of nature, rendering chemistry impossible and initiating a violent ontological reset of the cosmos. The equation of state parameter for dark energy dictates other topological limits. If dark energy exhibits phantom behavior, the universe ends in a big rip, where atomic nuclei are physically shredded. If the geometry is closed, the expansion reverses into a collapsing big crunch. Assuming the universe evades these structural terminations, it enters the black hole era, spanning cosmological decades 40 to 100. Black holes do not persist infinitely. As detailed by Stephen Hawking, the intense curvature of spacetime near the event horizon separates virtual particle pairs. One escapes, causing the black hole to slowly lose mass and evaporate. The evaporation timescale is proportional to the cube of the mass. The largest galactic mass structures will evaporate in 10 to the power of 100 years, culminating in brief, localized flashes of gamma radiation. With the final singularity evaporated, the cosmos is purged of its last structural landmarks. Without rest mass to serve as a clock or a measuring rod, space and time effectively lose macroscopic meaning. Beyond the 100th cosmological decade lies the dark era. The universe is an exceedingly diffuse gas of low-energy photons and massive, unstable positronium atoms drifting through an ever-expanding void. In 1979, physicist Freeman Dyson proposed a model for eternal intelligence, suggesting that an advanced civilization could survive this era. By adapting metabolism to the cooling ambient temperature, they could expend energy in decreasing fractions, achieving infinite computations with a finite energy reserve. Dyson's framework collides with Landauer's principle. Any logically irreversible operation, like erasing a memory register, must dissipate a minimum amount of heat. This minimum energy cost is strictly defined by ambient temperature. But the accelerating universe creates a cosmological event horizon emitting Gibbon's Hawking temperature. It will never reach absolute zero, stopping at 2.4 times 10 to the negative 30 Kelvin. Because the temperature floor never reaches absolute zero, Landauer's limit imposes a permanent non-zero energy cost for every single computation. A finite reserve of energy can only yield a finite number of thoughts. Furthermore, the de Sitter horizon actively removes causally disconnected regions. In approximately 150 billion years, all galaxies outside the local supercluster will be permanently isolated, severing access to external empirical data and resources. An accelerating universe makes survival a thermodynamic impossibility. Intelligence faces a rigid mathematical boundary. It must either burn out quickly or scale down its complexity until consciousness is extinguished. Theoretical physics contains models that attempt to bypass this terminal state. The most prominent is conformal cyclic cosmology, or CCC, developed by Roger Penrose. CCC suggests that the massless, scale-free void of the dark era becomes mathematically indistinguishable from the ultra-hot, dense origin of a new Big Bang. Through conformal rescaling, our infinite future maps on to the next iteration's microscopic origin. But this model fails thermodynamic accounting. Hawking radiation from black holes transfers disorder into the radiation field. Statistical entropy doesn't reset, it carries into the new aeon. The required conformal mapping also demands the universe become perfectly massless. This strictly requires the spontaneous decay of electrons, a theoretical process that is expressly forbidden by the fundamental conservation of electric charge. Geometric remappings cannot sidestep the second law. The available evidence directs to a single conclusion. The universe operates on a one-way trajectory toward maximum entropy. Organized matter, orbital mechanics, and computation are brief, highly structured anomalies driven by a finite gap in an irreversibly fading cosmos.